Anyway, yeah, you never know how live demos are going to go. What we're going to do is the Kafka as a platform stuff I was hinting at this morning. I want to go through that a little bit more carefully and talk about those components a little bit more carefully, and in particular, stream processing. That, I think, needs a little bit more attention. I'm going to give you a demo of the Kafka Streams API in Java. We're going to take two streams and aggregate one of them into a table and join it with a stream and do things like that, and ideally we'll actually get some coherent results out of that exercise. So that's pretty cool. That's our goal. So pay no attention to that title and its mismatch with the program. You are getting what the abstract says. Is anybody reading the abstracts? It's okay. I know how it goes. Right. I attend conferences too. You look at the title and you're like, that looks good. All right. So part of the goal here, part of the concern that Kafka is trying to address is this kind of mess. When you think of Kafka as an integration technology, like some of you have seen architecture diagrams that look like that and have been presented as good things, right? Like, hey, look, we built this. You should not get near a keyboard. But when you've got applications that are talking to each other in an ad hoc point-to-point way, then you get an architecture that looks like this. It's very brittle. It's hard to extend. Even if microservices are not what you're thinking about, if you just have application A with some ad hoc interface with application B, and you extend that to C, D, E, F, G, H, I, J, et cetera, you end up with something very messy. Our goal is Kafka as a central nervous system where applications and legacy databases and offline analytics systems can all talk to the thing in a coherent way. And like I was talking about this morning, we tend to have this tool set with databases. We build applications centered on databases, which is a data store, which is a place for data to go. Yet what a company is actually built on is event streams. So we want to try to come up with an architecture that, whether microservices are your concern or not, we want to think about events as first-class citizens and treat things this way. And I think we kind of covered this morning, but you think of like a retail business, it's very simple to see, to see that business in terms of event flows. You've got orders and sales and inventory being received and inventory shipping out and actual shipments going out and fraud detection, notifications and things, events like that being generated by the system. And we have this unfortunate illusion that we create of static data, as I said before, taking an event, serializing it, putting it into a place like the data would stay still, where what we really want is a model of explicit change. So with that in hand, let's think about streaming as a platform, not merely a pub subsystem, not merely a big queue, but a few elements that we have to have in place for this to be the kind of system that you could use to build companies on. And that's really the goal. I mean, it's one of those technologies where you can use it in a small way, and that's good, but the more things get on board, the more applications get on board with streaming, the more value you extract from the platform. So it is, in a sense, it's kind of like a viral technology. It's good to have two things integrated through streaming. It's good to have 6 services composing some little area of functionality integrated through streaming. But then the more things get on board that streaming backplane, the more valuable the platform is. So it does. There's this real sense in which, like, Kafka wants you, right? It's trying to absorb more and more of a system and deliver value to the components that get on board with it. And it's got a slightly bigger intention for the world than we've given it credit for. Anyway, this kind of platform, what components are necessary to make this work? Well, 3 of them. And I hinted at these things this morning. I want to talk about them in a little bit more detail to solidify them. Number 3 is really our goal in this session. stream processing. That's where we're going to go write an application and look at the Java Streams APIs. That's where we're headed. I want to make sure the platform is very solid in your mind, and then we're going to get to some live coding in the Kafka Streams API. So, and again, just to frame that, it's a very, very powerful API. If you're already a Java shop, there's no real friction. There's no real reason not to use it. There are all kinds of cool things about it. It's a little, in my experience and in experience just talking to developers who use it, it's got a learning curve. So people, is anybody using Streams right now in Java? Okay, so usually people who are like, see, there's two of you. Usually people who have made the investment are like, yes, Streams is awesome, and we're going to keep using it because this was not easy. It's an API that, would you agree, has some learning curve? Yeah, right. The documentation is getting better, trying. We're working on that. But yeah, it's got some learning curve to it. So even if you're a Java shop, you're going to find a lot of power in it as long as you're willing to make the investment. If you're not a Java shop, then as soon as I start with the Java code, you'll be mad. So I want to see who's going to be mad. Who is like no Java in your organization at all? Don't even care. Okay, good. Who's some Java? And all Java. Oh, okay, that's actually a pretty good crowd for this. Okay, sorry. But later, we'll get to KSQL. And part of this is you see the Java version, and in a little bit, when I talk about KSQL and do the demo with KSQL, then you really feel the value of KSQL. It's like if you took differential equations, you get like 2/3 of the way through the semester, and then you learn Laplace transforms. You know, you've been solving differential equations with all this horrible calculus, like this big, long, page-long slog to get to the answer to the non-homogeneous equation, and then they show you Laplace transforms, and it's like algebra that you did when you were 14. And you're like, you knew. This whole time, you knew, and you tell me now. So I'm telling you now, there's the Java API, and there's KSQL. And KSQL is going to feel like a much easier thing. Just so you know what we're all about here. All right. We need PubSub, we need storage, and we need processing. And let me tell you how the Kafka and Confluent platform deliver on those things and why you need them and really what they're all about. Now, logs, we talked about logs, you get the idea. You put stuff on the end, and in Kafka you have these other readers that can be consuming at other places in the log. We talked about the producer. In fact, multiple producers can be producing to one topic. We talked about consumers, but not quite enough, and I want to go into a little bit more detail. There was kind of some Q&A where I hinted at this, but I know I didn't make it clear, and this is important. So, consumers, just like producers, are programs you write that use a Kafka API or some community third-party API using the Kafka wire protocol. Producers put messages into topics, consumers take messages out. Focusing specifically on the consumers here. A consumer, so Kafka, so a broker is, in its mind, managing partitions. All right? A topic is a thing that gets broken up into partitions. Partitions are little slices of topic data that get stored on different machines, different brokers. And a broker, all it really knows is, hey, I've got these partitions. There's a little bit of metadata that says, well, here, this partition, number 1, 2, 3, 4, is associated with a topic called movie ratings. But whatever, I've got this partition. And what a consumer does is a consumer says, I would like any messages you have in that partition with offset X or higher. That's the consumer interface right there. So as a broker, I don't technically really know who's consuming my partitions. I get requests that say, here's a partition. Somebody is asking for messages of offset X or higher. Remember, every message in the topic is numbered. The first one is 0, the second one is 1, the third one is 2, and so on. They all have a numeric offset. The consumer asks for an offset. And so the broker is just sitting here saying, people are consuming stuff. Somebody asked for a thing. I don't have that thing. Like if you're asking for an offset past the end of the log, if I was trying to consume 10, or I'm a broker and somebody's trying to consume 10, I'll just say, I don't have 10. That's it. So as a consumer, or pardon me, as a broker, I don't really know who's consuming me. That's kind of nice. That way, as a broker, I get to have a little bit of simplicity in my life. As a consumer, I need to know what offset to ask for. That's what consumers do. Consumer says, I would like 10 now. And if by the time I get around to asking, if 10, 11, 12, and 13 show up, I'll get all of them. But I need to know that number. So what's good about that? Well, what's good about that is it keeps the broker simple. What's bad? What is absolutely terrible about that? Somebody say it. You're thinking it. Yeah.
The consumer needs to remember where it needs to take off.
It's a distributed state problem. So yeah, while the consumer is running and is not failing, that's fine, right? It's going to just keep it in memory. But the consumer is going to fail. It's going to go down. It's going to get upgraded. All kinds of things are going to happen to it. And now I've got this state hanging out in this distributed system that I'm building that I need to remember, okay? And that is bad. Just like all distributed systems are bad. Okay? If you guys, in fact, I wish that you weren't even interested in distributed systems and you were working on something simpler where you could go home at 3 p.m. and enjoy your life more. But here we are, all working in distributed systems. You're building this distributed system of consumers. They need to remember that offset. What they end up doing is storing that offset in a special topic in Kafka. So every once in a while, every few messages, when a consumer is consuming, it's going to write back to this internal topic called consumer offsets, saying, hey, I'm this partition, I'm a consumer called this, I'm this instance of the consumer, and this is my offset that I've most recently consumed. So the consumer goes down and comes back up. It can remember that it'll know what that last offset was. So you have this distributed state problem, and you use Kafka to solve that problem. So those consumers are able to remember their offsets in that way. If all three, as a consumer, by the way, I have a unique name. A required configuration parameter in the API is called group ID. And I'm a consumer, I have to have even if I only ever think I'm going to be a group of one, I still have a group ID. That's my name as an application. And if all three of these guys here had different names, app, and app, they would be different consumers managing different offsets. And so even if they're consuming from the same partition, they're going to be able to track different offsets in those partitions. Now, I hinted at this in the earlier talk, and I'm setting this up so we can go into more detail on this next thing, and that is consumer groups. This is a foundational technology in Kafka that gets reused in several places. As I said, every consumer is a group, but once I deploy a second instance of a consumer with the same group ID, like you see at the top there, I could have started with just one instance. If I add a second instance, then whatever partitions that first instance was consuming, say there were 10 partitions in the topic. Well, there's only one consumer, so he has to consume all 10 partitions all the time. If I add a new instance to the group, now 5 of those partitions are going to get reassigned to the new instance automatically for me. I have had to do zero work to make that elastic scaling happen. Cool. Because you ideally don't want to have to build distributed infrastructure. This one on the bottom has 3 instances, B, B, and B. Now imagine there are 3 partitions in the topic that group is consuming. I am now at the limit of my ability to scale that topic. If I add another instance to that consumer group, it has nothing to do because all the partitions are completely assigned, and Kafka won't split a partition between 2 consumers in a group. So that's one of the motivations for scaling a topic is the ability to scale consumption. So if you know maybe you have a topic that isn't particularly high bandwidth, or maybe you don't have a lot of data retention time or anything like that, so you think, I don't really need to scale this that much, but you have some extremely expensive consume behavior happening, well, that's a motivation for more partitions, because you want to be able to horizontally scale your consumers more. All of this is a good story, and almost too good to be true, because literally the only code I had to write to get access to this is I had to add a configuration parameter called group ID. I set my group ID. Well, frankly, a consumer won't start up if you don't, so it's cheating. But you tell the cluster what your group is, and you can scale elastically. I can even scale back. I can remove instances, and those partitions will be reassigned. I have some fault tolerance. Where does it go wrong? Well, if your consumers are entirely stateless, everything I just said is true. All of that goodness and the guarantees and the beauty of scalable consumer groups and your ability to make an elastically scalable fault-tolerant application just by typing a few lines of code, that's all true for stateless consumers. So if you're consuming some topic of transaction records and you want to filter it to only those transactions that are €5 or more and produce a new topic with large transactions that are filtered by that rule, that's fine. This works great. If you want to average transactions over the last 5 minutes, that's stateful. So stateful consumer groups are a little bit of a pain, and streams is going to rescue us from this. Let me explain why stateful consumer groups are a pain, if you're not already thinking it. Again, in here, this is the consumer API, so I just see, I have an API that gives me messages. I say, give me any new messages from the transactions topic, and when they show up, and I can iterate through them and imperatively do processing things on those messages. There are a couple of lifecycle events in that API that I can hook that will tell me if Kafka is about to take away a partition from me or give me a new partition. So I can be aware if a reassignment is happening. Obviously, I can't be aware if I'm going to go down. That happens without me knowing, but I can know when partitions are getting shuffled. But then if I've got internal state like I would for an aggregation or a grouping or a join or a window or some kind of operation like that, that internal state is in memory in my consumer, and I'm going to have to go do something with that. Consumer groups don't help you manage state in your consumer at all. So if you've got a stateful consumer, the goodness of consumer groups is just a little bit harder to access. And now there is distributed systems work you have to do. You have to manage that distributed state. I was giving this talk a couple months ago at a big US, I guess a bank, kind of credit card company / bank. And somebody in the audience said, well, couldn't you just put that in a distributed cache? And I said, well, that is spoken like a man who happens to have a distributed cache lying around, right? And yes, that's true. If you've got one, that works great. If you don't, that's kind of a crappy answer to say, well, this is fine. Just stand up a distributed cache and everything, well, gee, thanks, So this is how consumer groups work. It's an extremely powerful technology. It's a kind of a layer of Kafka that we build other things out of. But if you get into stateful work in your consumer groups, then there's a little bit of a wrinkle. And we'll address that in a little bit with streams. I'll give you the story there. Okay. Connect, I talked about this a little bit ago, that whole diagram there of Kafka in the middle talking to all those other things, as I gave you the illustration earlier, how if you just ran away and started building things, you'd build at least a database connector, and there'd probably be a few other connectors that you build. Connect is the framework that gets that done, and let me tell you a little bit more about how it works. So Connect is a server process that you stand up on client machines external to the cluster. And this is, drill into this language a little bit. So Connect is a part of Apache Kafka. It is a part of Kafka as a project. Infrastructure-wise, when we say Kafka, I mean the collection of brokers and the few Zookeeper nodes that are shamefully off to the side that we try not to. Everybody's got one in the family, It's that's ours. So there's some Zookeeper, and then there's the brokers, and that's Kafka, right? That pub/sub system. Connect is a server process that's running on machines that are not brokers. They are behaving as Kafka clients, which means, answer this question in your mind if you don't want to answer it out loud. If you're Connect, how are you talking to the Kafka cluster? produce and consume. Always the answer is produce and consume. It's the only way you can talk to the cluster. What can you do? You can produce messages, you can consume messages. Those are the things you get to do. And Connect does those things. It just does them for you. So Connect is this server process. As we discussed earlier, there are source connectors that read from some external system and produce into topics. There are sync connectors that consume from topics and send messages to some external system. Examples, S3, HDFS, Elasticsearch, relational database sync connectors. I think there's a Cassandra sync connector. Source connectors. You've got, well, there's a community Twitter source connector that's deeply practical. Everybody needs to consume tweets in their enterprise application. It's a nice piece of example code and awesome for Connect conference demos, you know, because you have people like tweeting with a conference hashtag and it shows up in the topic. It's cute. A nice example, but not super practical. But usually people are sourcing from relational databases, and there's a whole catalog of those available on the, at least of the Confluent supported ones and some of the community ones on the Confluent website. We've got a list of them. Now, so it's the server process. It's running external to the Kafka cluster. It is scalable. So if I have a large Connect workload I need to execute, I can have 5, 10 Connect machines partitioning the input workload in whatever way is appropriate for the input workload. Some input workloads, of course, are not partitionable. For example, if I'm consuming from a single relational database table, can't really partition that, right? I just have one worker reading from that table. But if I'm consuming from 5 different relational database tables, each table is itself a partition and could be managed by a single Connect worker if I'm scaling out my Connect cluster. Since Connect scales out, it actually borrows that consumer group functionality that I was talking about to assign partitions to workers. So a Connect cluster acts kind of like a consumer group. And so if you add a node to the Connect cluster, it can get partitions assigned to it. If you remove nodes or nodes fail, partitions fail over from those into the surviving nodes. And input offsets. So if you're reading from a relational database, there's a maximum ID or timestamp or something like that that you're looking for in your next message. That offset is managed by Connect and stored in an internal topic in Kafka. So all that kind of stuff. Your basic scalability and fault tolerance is baked into Connect. Connectors are themselves, I mean, fundamentally they're jar files. It's a Java API. And most of the connectors that you're going to need in typical enterprise work are already done for you, like I said, either in the community or in our officially supported versions. They are almost without exception open source. We have a couple of them, like the, there's a JMS connector. I think JMS connector, yeah, I think that's not open source. That's a part of the enterprise offering. I guess we figure if you're using JMS, you should pay. I mean, one might argue you already are, and we're just adding insult to injury, but they're mostly open source. If you wanted to write your own, I mean, there's the API is not complex. If you have to write your own, if you're connecting to something that's not standard, it's pretty simple to do. So that's Connect, and what else am I saying? Oh, I just said all these things. This is basically what you get. Feels like I'm missing something important about Connect. Oh, yeah. Just the notion that it's declarative, right? So you make sure that the actual Connect code that you want to use is deployed to your Connect cluster. So, you know, that means there is a jar file you put into a lib directory somewhere. And most of the usual suspects are already included with Connect, but if it's some third-party thing, like the Twitter thing, you know, you're going to have to build that jar and dump it somewhere. And then actually to kick off Connect, there's a REST endpoint. You throw a piece of JSON at it that has configuration parameters, and Connect says, oh, okay, I'll talk to that thing. I'll produce to that topic, or I'll consume from that topic, and I'll dump your data into a file, or whatever it is you've told it to do. So pretty easily automatable, and basically a nice thing. We talked about JDBC, we talked about all of those. Let's talk about storage. So This is worth hammering on. I know I said this morning already, but there is, I think collectively we have a little bit of a reluctance to believe that Kafka can store data long term. There was a fascinating thread on Hacker News, he says, last summer. So I have this hobby. I like to take time lapses. And time-lapse people, if you know any of them, the goal of the time-lapser is a day-to-night or night-to-day transition. It's real challenging. There's like a massive change in brightness, and you have to adjust the exposure. There's all this software you use in post-processing to make it all look pretty and everything. It's super cool. The day-to-night, night-to-day thing is called a holy grail time-lapse. And there I am at a park near my home, looking at the beautiful Rocky Mountains and the sunset, adjusting the exposure on my camera, doing this time-lapse. And I had my computer open, and I was tethered. So I was there, Slack was running, and I get a message from my boss saying, hey, there's a really interesting discussion on Hacker News. You should look into it. I'm like, well, it's the thing about, I think, leading a happy life is that you don't read the comments on Hacker News. But there I am, and I jumped into it, and it was on a blog post of ours that had to do with data storage in Kafka, and there was this collective refusal to believe that Kafka could actually store data. They were just like, no, you can't. And in fact, it can. So by default, a topic, remember what a topic is. A topic is broken up into partitions, and a partition is a log of messages stored on a broker. That log is replicated to other brokers, but let's just focus on one right now to keep it simple. After a certain file size, the broker will roll to a new segment, because you don't want files that are too big, and then you roll to a new segment and roll to a new, it's all fine. We do this with application log files, no big deal. Each message, of course, is time-stamped, which lets us say, once there's a particular segment whose newest message is older than some time limit, we can expire that log segment. We can have a data retention period. The default data retention period is 7 days for Kafka. So after there's a log segment whose newest message is 7 days old, we can drop that log segment off the edge of the world and just delete it, okay? You can set the data retention period to -1, which means forever. Don't ever expire log segments. Keep data infinitely. Now, there are probably legal professionals in your company who would ask you not to do that, because there's the whole data retention thing, which interacts with regulations, and you guys have some interesting regulatory things going on here with respect to data retention and privacy recently. Thanks. You don't usually literally want to keep data forever, but the point is it's possible in Kafka. It's possible to have data retention be infinite, and you're storing log messages on disk, and you're replicating them to other brokers. And this is what we mean by data storage, right? You store it on disks, and you replicate it. And this fascinating thread, the conclusion of the thread was no, not really, because it's a queue. And what if you misconfigure it? What if you accidentally set the data retention period to something shorter? Well, then you're probably not going to retain your data. That's like accidentally allowing delete permissions on a table that shouldn't have delete permissions and somebody deleting a bunch of data. It happens in the world, right? But the point is not that Hacker News is a dangerous place, but the point is, yes, Kafka is, in a sense, a queue. It is a messaging system, but it is an unusual one in that it also stores data durably and for the long term. So that's a very long way of saying that simple statement, but sometimes that simple statement is hard to believe because queues are supposed to be ephemeral. And you can make Kafka expire data very quickly, but it doesn't need to. So it is, in fact, a data storage system. You always have constant time writes. You can have very dense nodes. There are some things, for example, HDFS. You can also make very dense nodes in HDFS. You can have many, many terabytes on a data node in HDFS. Cassandra, if you know anything about Cassandra, it gets a little tough to make a node too dense. There's some overhead that Cassandra has to maintain really in memory for anything that it stores on disk. And that means you never see a 40 terabyte Cassandra node. It's just not a thing. But you can do that with Kafka if you want. If you really want to load the thing up with disks, a broker up with disks, you can have lots of storage, commodity hardware. It is fine. And it's fast because it's not doing much. You know, you're putting messages on the end, or you're seeking and reading messages from inside a topic, and often the messages you're reading are really all in the same part of the topic, and so caches tend to work well, and so on and so forth. I am not going into any kind of detail about how replication works, but I will tell you a quick story about that, just so you have some idea. Any production instance of Kafka, you're going to have data replicated, and this is one of the things that, well, you know, we solved the problem of data loss due to hardware failure and created a bunch of new problems. Once you've got copies of things that change, you have to manage consistency of those things, right? But Kafka replication does that. Basically, say I have, again, we think at the partition level, not really the topic level. So I have a partition of some topic, and that topic has a replication factor of 3, which means I'll have that topic stored on 3 brokers. And one of those brokers will be elected, will elect itself as the leader. The others will be the followers. So anybody, any producer who writes to that partition actually connects over the network through a socket to the leader, and the leader does the write, and the leader manages the replication to the followers. Anyone consuming from that partition actually uses a connection in the connection pool to the machine with that leader partition on it and reads from that leader. So all I/O is always on the leader. And the leader manages replication and consistency with the followers. And we'll just, yeah, that's a nice simplifying assumption. There are still some complex edge cases in there that have to do with consistency. There's still some tuning parameters on the produce side about what constitutes a successful write, but all that is handled. We have a good replication story and a good fault tolerance story there. Let's talk about stream processing. So, as I said before, it would not do to have to use only the producer and the consumer APIs. For some things, they are entirely appropriate, but often we find that if you look at the evolution of Kafka over time, the community, the open source project, this isn't even like Confluence roadmap, this is the community keeps inventing these layers that are trying to keep you from using those. And if you look at, it was late 2015 in Kafka 0.9, Connect came out. Connect is an attempt to keep you from having to directly program consumer and producer code. It's doing it for you declaratively with these nice plug-in modules. If you go forward a little bit, Connect or Kafka 0.10 in, I think it was May of 2016, that's when the Streams API came out, and that's what I'm going to be showing you about in the next little bit and actually attempt to build an application with. The Streams API was an elaborate attempt to keep you from having to use the producer and the consumer API, instead to give you this rather beautiful, rather functional, effective functional API, functional in the capital F sense, which you'll see when we get into the code. And since then, we've added KSQL, which is an attempt to keep you even from having to write Java code. So revisiting this morning, just to give you an idea of the place that Streams kind of puts itself into, metaphorically, again, thinking of kind of back to the microservices world. There are certain services. If you think of life as a hotel, there are certain things. This is an easy one, an easy metaphor for me, because I spend about half of my year on the road, so I know a lot about hotels. There are services that have to exist in a hotel. There's security, there's the front desk, there's probably a kitchen, there's housekeeping. My hotel, there's a room, special room dedicated to ironing. That's its own microservice, the ironing microservice. I would like to subscribe to that service. Yeah, all these things need to be orchestrated and scaled independently. Just this is the world of microservices. I need security, I need room service, I need reception. These are all independent applications, but I also need to be able to scale them independently. And each one of those is dealing with common data flows, just like we looked at this morning. And sometimes the transformations that they have to do are non-trivial. Like security is probably going to have access to parts of the data that maybe reception doesn't. Like maybe reception can't just break into my room. Security probably can. Housekeeping can get access to my room and move things around and put new things in. And these things all need to scale differently. Now, if again, the basic idea here is that as enterprise developers, if that's what you are, you want to be able to focus on application development and not infrastructure. Like you want to be the security team, or you want to be housekeeping, or you want to be the front desk or the kitchen, and you want to be really good at that and not the rest of this infrastructure about how to hire people and fire people and pay for things and do payroll and all that kind of stuff. You want to just be good at the thing that you do. Building infrastructure is, as Admiral Akbar would say, a trap, because it's one of those things, just like frameworks, that's more fun. It's much more rewarding sometimes to take a break from the craziness of business requirements that seem so random and force so many special case, little this, that, and the other thing, bits of code, and build a beautiful piece of infrastructure that solves an interesting computer science problem. It's fun, but it's a temptation because this does not add value directly to the business. You can get in trouble for that. So anyway, in building these business applications, though, we're expected to build things that are elastically scalable. And that's kind of just what we call table stakes now. That's what it takes to get to the table, is to have an elastically scalable application. And that's fault-tolerant, where nodes can go down. You can lose instances and things still work. We don't want to be limited by the consumer group sort of preference for stateless applications. We're going to need to be able to handle stateful processing. Of course, really what we're saying is we're building distributed systems. Now, Matthias was talking about this a little bit in his talk, the way Streams handles these problems and handles state. Do you remember that? He was talking about RocksDB and the internal state store, all that stuff. I'll get to that in a little bit when we're looking at the code. I'll remind you of that, but you should have gotten a little bit of a primer on this earlier. There's another interesting question that comes up in stream processing frameworks, though. Because as Matthias was talking about, Kafka Streams is not the only one. There are other ones out in the world. And they have different opinions about how to build systems. And I think this is a very, very important thing when you think about Kafka Streams. Pay attention to what I'm about to say here, because there's a seemingly strange architectural opinion that Streams has, but it turns out to be brilliant. So, trust me. The first question that the stream processing frameworks present us with is, where am I going to do my computation? So, for example, Flink, native son of this very country. Flink is absolutely one of the first-class open-source stream processing frameworks in the world right now. Very important piece of technology, very sophisticated piece of technology. Its opinion is you're going to write a stream processing job, and you're going to deploy that job to a cluster of machines. Your compute is going to be done in the Flink cluster over there. You write the job, you deploy it there. Now, I've got some application that's trying to use the results of that stream processing, but you deploy it there, and the rest of your application, whatever it's doing with the results, that runs over here. So you've got your Spring Boot web front end or REST front end or whatever it is. The stream processing is not running here, it's running over there. So the first question is, where does my compute go? This question comes from, I think, if you look at the legacy of distributed processing frameworks in the last 10 years, it kind of starts, or 11 or 12 years now, it starts with Hadoop, which was really three things. It was this really, really good distributed file system, that's HDFS, that's a cockroach, okay? If a nuclear war destroys us all, there will still be HDFS clusters running, probably still new HDFS clusters deploying themselves somehow. It's never going to stop. And it shouldn't. It's not like it's a bad thing. It's a fine distributed file system. So Hadoop was that, and then Hadoop was the MapReduce API, to be able to do computation over that data. And then it was a job manager to move my MapReduce functions around and keep track of what was running and try to optimize where things are, right? So file system, API, job manager. And the whole idea was I had a storage cluster. Why? Because I need a storage cluster, legitimately, and I want to do compute over that storage. So now let me have a job manager that moves my map and reduce functions around and shuffles and does all that work. I had to use, or it made all the sense in the world to do my compute in a cluster because my storage started as a cluster. So there was nothing bad about that idea. It changed the world. And these days, nobody writes new MapReduce applications now. We realized it was like getting hit in the head with a stick. And so new things have evolved to take its place, like, for example, Spark. Okay, if you look at the Hadoop vendors, what are they selling? They don't talk about MapReduce a whole bunch. They talk about Spark a lot. So Spark is the new distributed computing API that will still run on your HDFS cluster. So I've got this cluster out there. That's the assumption. Here's this cluster with my data. Now let me go do my compute on that data. Spark is conceptually, architecturally exactly the same thing as MapReduce, just with an API that does not make you want to die. It's an API that makes you feel like a programmer that can get work done. So again, I absolutely have nothing against Spark. It's the right way to do batch processing right now. So contemporary stream processing frameworks take that set of assumptions, like we're all in this mood of we've got this processing cluster, and now I need to be a stream processing framework. Let me stand up a cluster so I can do my stream processing work. You know, I'm going to have a cluster anyway. Let me make this new kind of class of infrastructure to do that. And that's the basic assumption of Spark Streaming and Flink, is that I'm going to have a cluster to do this work. Spark Streaming has, there are other issues at play with Spark Streaming, but basically one of the core differentiators between Kafka Streams and Flink is Flink has this opinion that we have a processing cluster. The real question being not where's my compute, but where's my code? And I think there's an operational angle to this. Just by virtue of my background, I always think of the developer angle before the strictly ops angle. But if you're going to do stream processing, sometimes you're just going to write a program that says, let me ingest this topic, do things to it, and put out a new topic. And that's fine. And frankly, that's KSQL, which I'm going to talk about later. KSQL works that way. That is not a bad thing. But if you're writing in Java, and you've got an application that does stream processing as an add-on to some other thing that it's doing, some other interface that it's responsible for, then it doesn't make sense to take my stream processing code, rip it out, stick it over there, deploy it through this other mechanism that's fairly brittle and is only going to ever work one way, and then here's my Java application. Let me deploy that with my super automated push button, continuous delivery, automated elastic scaling Kubernetes. There's probably, you guys all do that, right? No, but you want to, and you want to grow in that way. So Streams has the opinion of, let's just be built in. All right, it's an API, a Java API. It's a jar. It's a Maven dependency or Gradle dependency that you program directly. And so if your application is doing other things, where does your stream processing code live? Lives in your application. So conceptually, now as a developer, you're able to think of that as a whole. Operationally, you're able to deploy that as a whole. How do you deploy it? Do you build a war and drop it into a Tomcat 4.1 hot deploy directory? Fine, we can be friends. You can do that. Or do you do the super cool next generation automated thing? Or are you somewhere in between? Streams doesn't care. You deploy your Java code. It's Java code. You do what you want. Kafka is always trying to stay out of your way in terms of what your deployment looks like, and that's the case with streams. And that is, I think, the most important architectural opinion of streams. It's not the API. The API is what it is. It could be different, but all the stream processing APIs kind of do all the same things. It's not the state management. The state management is great. Any state that you accumulate in the app as a result of your stream processing is, as Matthias was saying, it's stored in an internal lightweight key value store that's persisted to disk and persisted back into Kafka. So you need to fail over, does one of your stream processing nodes go down, you need to move those partitions somewhere else, it's okay, you have the state lying around. It takes advantage of Kafka's exactly once semantics and the internal transaction API to give you effectively, I think effectively once was our Swedish friend Victor's tweet, effectively once processing, which is exactly what Kafka Streams does. So it does all those things, and those are great. And again, those are sort of what you need to be a modern framework. Its distinguishing feature is it's an API, and it doesn't get deployed to special infrastructure. KSQL is as we'll see later, tries to be as similar as it can to that. It's a slightly different view of things in exchange for the simplicity. But basically what you need to know is your streams application does not run in brokers ever, and this is a thing that I often have to say several times because it was certainly my assumption when I first learned about Kafka Streams, like, oh, that's great, we can make those brokers get warmer and deploy our code in there, and the people running the brokers are like, oh, no, you can't. You can't put any code here. That's adorable, but not going to happen. You scale it out, and it scales like a consumer group, right? You just add more instances to the application. Except now it's handling the stateful problem for you, so all the nastiness of scaling stateful applications as consumer groups gets handled. The question?
Yeah, there's just some fancy stuff in terms of dynamic partitioning in case you do some applications and stuff inside the DSL.
It's not, I wouldn't call it fancy.
Okay, some kind of automation or
You get,
configuration on my behalf.
so here's what happens. Suppose, I'll make up numbers. I'm one instance, so there's just one instance of the application, 5 partitions in a topic I'm consuming. There will be 5 threads, and those get spawned for me. If now I have 2 instances, then there'll be 3 threads on one and 2 on the other. Another question? No, okay. So yeah, it's fancy in the sense that that process is automatic.
Okay, but if I spin up some more, it doesn't do it like auto reconfiguration.
It does. No, I'm sorry. If I now dynamically add another instance of the application, it'll move. And think about this. This is actually the important case because there's 3 threads over here, and one of them is going to get moved over to here. Well, there's state. There's a RocksDB instance associated with that. So what that will do is the persisted copy of that RocksDB instance in the internal topic can now be used to hydrate this guy. And I get the state, basically, which I would not have gotten without streams. So absolutely key. All right, let's just go to coding. Hey, if you like what you heard there about streaming platforms and how Kafka and the Confluent platform work, be sure to like the video. If you have a question or a comment, you know where that goes down below. As always, you must subscribe to the channel. And if you want to see some more, if you want to see a live demo of Kafka Streams in action, check out the next video.